Hey, how you guys doing? So, got some new markers ready to rock and roll here. This is going to be 4.4 part 1. So Ryan already did more algebraically. I'm going to focus a little bit more graphically for you guys. Okay, but a couple things we do need to talk about, or at least review, because I know we have done limits in the past when we're doing graphs. Alright? So, this is the limit of f of x as x approaches c. Okay, so that's exactly how you would read that. The difference here, we got a little negative, almost kind of as an exponent. I guess it's kind of hard to see there. Alright, it's like this little negative in our exponent area. So this is going to be read as the limit of f of x as x approaches c from the left, alright, because negatives are on the left, so that's one way to remember it. And then if we have a little plus as our exponent area, okay, this is going to be read the limit of f of x as x approaches c from the right now, okay, because positive numbers are over on the right. So, the limit of f of x as x approaches c from the left, okay, it must equal the limit of f of x as x approaches c from the right for the limit of f of x to exist as x approaches c. Okay, so basically what I'm saying here is we have to approach the same number on the left as we would on the right side for the limit to exist at a specific point. Alright, so I already drew up an example here. It's a rational function, you guys' favorites, I know. We got x plus 2 over x squared minus 6x plus 9. So the first thing, if you guys are going to be asked to graph this, would be to factor the top and the bottom. The top is already good, isn't it? This bottom, though, we got to factor yet, so we've still got x plus 2. Now we're going to get x minus 3 times x minus 3, which is x minus 3 all squared. Okay, so remember rational functions, we have vertical asymptotes, alright, where our denominator is going to be equal to 0. So in this case, we've got a vertical asymptote at 3. Alright, remember horizontal asymptotes. We're going to have horizontal asymptotes, we're going to look at our degrees. Is my degree bigger on top? Is my degree bigger on bottom? Or my degree is the same? So my degree looks like it's bigger on the bottom, right? Squared, so my degree is 2 on bottom. My degree is 1 up on top. Which means we're going to have a horizontal asymptote at 0. Okay, and as long as we're talking about rational functions, let's get into the x and y intercepts, shall we? Yeah, I think so. So remember your y-intercepts. How do you find a y-intercept? You plug x equals 0, because x equals 0 on your y-axis. Okay, so we plug in 0 for x. We're really just going to be left with 2 over 9 there. So that's going to be somewhere in here. That would be at 0 comma 2/9. Alright? X-intercepts. You find x-intercepts by setting your top equal to 0. Really, we're setting y equal to 0, but we can kind of cheat. And we just get our top equal to 0. So we have an x-intercept at negative 2. So it's going to be negative 2 comma 0. Alright, so as far as graphing this goes, guys, you could do sign analysis. Okay? Let's just do that for a little extra practice, huh? So if we do some sign analysis, okay, remember, really the values that we care about are going to be x-intercepts and vertical asymptotes. So we've got negative 2 and a positive 3. Okay, you can just plug in any number you want that's not negative 2 or positive 3. 0 is a good one, isn't it? We already know it's going to be positive at 0. So I'm going to put a big plus here, because 0 is in between negative 2 and 3. So we're going to be positive here. Okay, we can think about a rule of multiplicity to figure out the rest of it. Negative 2 is an x-intercept. It only occurs once. Okay, so what's going to happen is we're going to go through the x-axis, meaning we're going to be negative on the left side of -2. Over here, we got a vertical asymptote at 3. Okay, it's really occurring twice, so it has even multiplicity. So it's like bouncy, bouncy. So we are positive, we're going to stay positive. All right, so you could have done that without doing sign analysis, but you guys are going to have to get better at sign analysis, all right? Because you could have just looked at this graph, these intercepts, known that these two have to connect. Here we don't have any x-intercepts. Okay, so we can't go down to this asymptote, we're going to have to go up to it. Over here, -2 occurred once. Okay, so you don't bounce them out, so you're going to go through. But the thing is, we got to come back up to this asymptote. So it's going to look something like that. Over here, our vertical asymptote we said occurs twice. Okay, so we're going to stay positive. So my graph is going to look something like that. Got the volcano going on over here. Okay, so we really have 4 different limits we can describe these asymptotes with. The first one, this is really the limit of g of x as x approaches -infinity. Okay, so as we go further and further left, our y value gets closer and closer to 0. Let's do our other end behavior here. Okay, so this one is going to be the limit of g of x as x approaches positive infinity. Okay, so as x goes further and further to the right, y gets closer and closer to 0. Now we've got 2 of them here. Okay, this one is going to be the limit of g of x as x approaches. Okay, x is approaching 3 now, and it's approaching it from the left, so we want like a little negative there as our exponent. Okay, so as we're approaching 3 from the left, y gets higher and higher, y is approaching infinity. So the limit of g of x as x approaches -3 is infinity. Okay, as we talk about this guy, this is going to be the limit. Wow, that looks funny. Yeah, limit of g of x as x approaches 3 from the right. Okay, so now we're approaching 3 from the right side. X is getting closer and closer to 3, y keeps going higher and higher. Y is approaching infinity. So the limit of g of x as x approaches 3 from the right is infinity. Okay? Do you see here we have the limit of g of x as x approaches 3 from the left is the same as x approaches 3 from the right? Could even write that. The limit of g of x as x approaches 3 from the left equals the limit of g of x as x approaches 3 from the right. Therefore, the limit of g of x as x approaches 3 is going to equal infinity, because this all equaled infinity. Alright, so guys, as long as you're approaching the same value from the left as you are from the right, okay, then the limit of g of x as x approaches that point is going to be whatever those limits were. Make sense? Piece of cake? I think we're on to some more difficult graphs, maybe. All right. Let's see what we got next. Ooh, another rational function. Okay, so let's talk about h of x equals 3 minus x over x plus 1. Okay? So guys, go ahead, see if you can graph this on your own. You should be able to. All right. Okay, pause the video if you need to, see if you guys can graph that. All right, we're back. All right, so So guys, we got to figure out vertical asymptotes, horizontal asymptotes, all that fun stuff again. So we can't factor this, all right, it's already linear terms on top and on bottom. So remember, vertical asymptotes are going to be when our denominator is 0. So we're going to have vertical asymptote at -1 here. Okay, horizontal asymptotes, we got to think about our degrees. Here, my degree on top is 1, my degree on bottom is 1, so it's going to be the ratio of the leading coefficients. Okay, my leading coefficient on top is -1, my leading coefficient on bottom is 1, -1 over 1 is going to be -1. Alright, let's talk about x-intercepts. X-intercepts comes from setting y equal to 0. Here it's just going to be setting the top equal to 0. We have an x-intercept at 3. Alright, so then we got y-intercept. Remember, you find your y-intercepts by setting x equal to 0. So it's really going to be 3 over 1. So that's going to be at 0, 3. Okay, let's talk a little sign analysis again, shall we? Now let's hop over here. Okay, remember the only values that we care about on our sign analysis are going to be x-intercepts and vertical asymptotes. So we've got one at -1. We're going to have one at 3. Okay, I'm just going to plug in 0 again because 0 is nice and easy. All right, because we already know that's going to be positive at 0. All right, both our vertical asymptote and our x-intercept, they each only occur once. So all of our signs are going to switch every time. Okay, you didn't really need to do sign analysis if you're actually graphing this though, because hopefully you guys recognize that these two have to connect. Okay, here we're going to go through our x-axis because it only occurred once. Also, we have a horizontal asymptote down here at -1. We have to approach that asymptote. Over here, it's not going to go down to the asymptote because we don't have any x-intercept between 0 and -1. So we got to go up. Yeah. All right, and it makes sense that we're going to be negative now. Okay, because if we were positive, wouldn't we have to cross the x-axis? So we're going to be on this bottom part. Awesome. So guys, we're going to talk about 4 different limits here again. Let's start with our end behaviors. All right. So here, this is going to be the limits. Okay, we got h of x now. As x approaches -infinity, so x is getting more and more negative, we go further and further to the left. Y is approaching -1. Over here, we're going to have the limit of h of x. Okay? As we go further and further to the right, x is really approaching infinity. As x approaches infinity, y is approaching -1. Okay, now let's talk about this vertical asymptote. So here, I'm going to begin with my left. This is going to be the limit of h of x. As x approaches, okay, so now that we're approaching -1, we're approaching it from the left side. So you have a little negative there. Okay, so x is approaching -1 from the left. So as we go closer and closer to -1, our y value keeps going further and further down. So it's going to be approaching -infinity. Okay, if we talk about the limit of h of x, as x approaches -1 from the right, okay, so now we're approaching it from the right side, right? X is getting really, really close to -1. Y keeps going up higher and higher. So the limit is going to be infinity. Okay, now my left-hand limit does not equal my right-hand limit. Okay, therefore, the limit of h of x as x approaches -1 does not exist. Yeah, the limit does not exist. Okay? The limit does not exist. The limit does not exist. All right? Okay, guys, so if you're approaching a value from the left and a different value from the right side, then our limit as x is approaching that number does not exist. Now our left-hand limit still exists, our right-hand limit still exists, but the limit at that point does not exist. All right? Let's do some more practice. Yeah. Let's see what we got next. Ooh, let's go back to f of x now. Alrighty, yeah, we got f of x equals x plus 1. Okay? Let's find the limit of f of x as x approaches, well, let's do 3. Alright? So we can think about what this looks like graphically. Well, graphically, x plus 1 is linear. We got a y-intercept at 1. All right, a slope of 1. So we go up 1 over 1. Okay, so we're going to start here. And then we just go up 1 over 1 forever and ever and ever. Okay. All right, so if I were to make a table out of this, so guys, you don't need to make a table. Okay, I just want to get my point across. So if I talk about my left-hand limit here, the limit of f of x as x approaches 3 from the left. Okay, so what I'm doing here is I'm going to plug in values for x that get really, really close to 3. Okay, so one number might be, remember I want to approach from the left side. So isn't 2.9 pretty stinking close? Okay. So if I plug 2.9 into my function, I'm going to get out 3.9. Yay! But I think we can get a little bit closer. So if I were to plug in like 2.99, isn't that closer to 3? What I get out is 3.99. Let's get even closer. 2.999. Plug that into my function. I get 3.999. One last time. 2.9999. If I plug that in, I'm going to get 2.9999 plus 1, making 3.99999. Alright, so guys, what I'm getting out of this is basically as x is approaching 3 from the left side, isn't my y value getting really, really close to 4? So limit of f of x as x approaches 3 from the left is going to equal 4. Okay? Let's do the same thing from the right side. So let's find the limit of f of x as x approaches 3 from the right. So guys, once again, I'm going to make a table. You don't really need to make a table, but I'm just trying to get my point across. We got x, we got f of x. Okay. So now I'm going to plug in values that are really close to 3, but I want to do it from the right, so I don't want to be bigger than 3. So maybe like 3.1. Plug 3.1 into my function. 3.1 plus 1 is 4.1. Okay, a number that would be even closer to 3, though, wouldn't that be like 3.01? Plug that in my function. I get even closer to 4. Okay? I can even plug in like 3.0001. I'm going to get out 4.0001. Okay, so really all I'm trying to say here is that the limit of f of x as x approaches 3 from the right is going to equal 4. Okay? So basically the limit of f of x as x approaches 3 from the left equals the limit of f of x as x approaches 3 from the right, which equals 4. Therefore, the limit of f of x as x approaches 3 is going to be equal to 4. Okay, so my left-hand limit equals my right-hand limit, therefore my limit does exist at 3. Alright, that makes sense. As you guys do this, okay, what you're going to find out is you can just do direct sub. I can plug 3 into this function, 3 plus 1 makes 4, and we're all done. Okay, but we just got to talk about it graphically too a little bit here. Hey, let's do another one! Alright. That was too easy. We need to go back to rational functions, right? Check this guy out. G of x equals x squared minus 4 over x minus 2. We need to find the limit of g of x as x approaches 2. Okay? So we gotta think about what this graph looks like. Okay, because we're doing this graphically, not algebraically. Alright, so I have to figure out how to graph this. Guys, do you recognize my degree is bigger on top than it is on bottom? We don't have a horizontal asymptote then. Okay? What I do want to do though is factor. Factoring's fun. X plus 2 times x minus 2 all divided by x minus 2. So what happens with this? My x minus 2's cancel. Okay, so my graph is going to look like g of x equals x plus 2 if x does not equal 2. Okay, because what's happening at x equals 2 is going to be a point disco. Remember, if your factors cancel, it's a point discontinuity. Alright, so let's go ahead and graph this guy. So it's really going to look like x plus 2. Okay, so my y-intercept's at 2. I go up 1 over 1. My graph should look something like that. However, I do have a hole in my graph at 2. Okay, remember to find the y value of that, we plug that x value that canceled. Okay, so x equals 2 is my point disco. Plug that into what remains now. X plus 2. So 2 plus 2 makes 4. Okay, so my point disco here is going to be at 2 comma 4. Okay, so I'm going to skip over making the tables. I think you guys get the idea, right? So what's happening here, as I approach that value of 2 from the left, y is getting really, really close to 4. It doesn't actually ever get to 4 though. As x approaches 2 from the right side, we're getting closer and closer to 4 for our y value. But it doesn't actually ever get there, right? Because there's a hole in our graph. So, the limits, we got g of x now, as x approaches 2 from the left, equals the limit of g of x as x approaches 2 from the right. These all equal 4. So guys, don't freak out that it doesn't actually get to that value, okay? We don't really care. I'm not asking you what g of 2 is. G of 2 is undefined. What I'm talking about with limits, all right, as we approach from the left and as we approach from the right, does that y value get closer and closer to the same number? Here it does. So therefore, the limit of g of x as x approaches 2 is going to equal 4. Okay? Now let's say there's another point here. Okay? My limit is still going to be 4. I don't care that we got a point somewhere else. Okay? What I care about is what are we approaching from the left and what are we approaching from the right. Okay? As long as those y values are the same, we're getting closer and closer to the same y value, that's all that really matters for limits. Okay? Let's do one more problem, a piecewise graph. Okay, you guys just had a test and you had to do a piecewise graph on that test, so you should be experts at this by now. H of x, yay! Okay, h of x is going to equal, we'll say x plus 2. If x is greater than 1, we're going to say 2. If x equals 1, and we're going to have x if x is less than 1. Okay, go ahead, so you guys can graph that on your own, so pause the video. Okay. Alright, so hopefully you guys are back. We can talk about graphing this. So, I'm just going to start with x equals 1. My y value is 2. Okay, that's basically saying that h of 1 equals 2. Same exact thing. So when x is 1, our y value is 2. Alright, so I'm going to start with the bottom here. My graph is x, y equals x. Does not just have a y-intercept of 0 and we go up 1 over 1. And we want this when x is less than 1. Okay? I don't want to include that value, so this is going to be at 1 comma 1. Make sure you label that. Over here we have y equals x plus 2 if x is greater than 1. So that'd be like a y-intercept of 1, 2. I go up 1 over 1. Kind of up in that direction forever. So this point's going to be at 1 comma 3. Okay, so let's talk about our limits here. My limit, I'll leave it right down here. My limit of h of x as x approaches 1 from the left is going to be equal to 1. Over here, my limit of h of x as x approaches 1 from the right, because x is getting closer to 1, we're doing it from the right side, this is going to be equal to 3. Okay? What I didn't tell you is what we're trying to find this whole time. What I want to know is what is the limit of h of x as x approaches 1. Okay, hopefully, maybe you guys were able to figure that out. So anyways, our left-hand limit equals 1, our right-hand limit equals 3. Okay? I don't care about this point at all. All I care about is my left-hand limit and my right-hand limit. My left-hand limit, my limit of h of x, as x approaches negative 1, not negative 1, as x approaches 1 from the left, does not equal the limit of h of x as x approaches 1 from the right. Therefore, the limit of h of x as x approaches 1 does not exist. The limit does not exist. Okay? So guys, like I said, you can have left-hand limits existing, you can have right-hand limits existing. They have to equal each other for the limit to exist at the points. Okay? Ryan will use a little bit different notation. You guys can use whatever you like. Instead of restating this, she'll say left-hand limit does not equal the right-hand limit. Okay? She'll say with the proper limit notation over here, as you approach from the right, as you approach from the left. But in their justification, she typically uses LHL does not equal RHL, or LHL equals RHL if it does exist. Okay? I always just use this because I'm not lazy. Although this is proper notation. Last thing, guys, like I said, this point does not matter. That point could have not been there. It still doesn't exist. If we filled in this point, my left-hand limit's still 1. My right-hand limit's still 3. It doesn't matter if that point exists or not. Okay? My limit would still not exist. We don't care what the actual value is at 1. We don't even care if it exists. Okay? All we care about is what are we approaching from the left? What are we approaching from the right? What are those y values? All right. Hopefully that helps a little bit. That's going to be it for now.